All right, this is another good comparison between the innate immune system and the adaptive immune system. I like this because it kind of gives us a visual representation. The innate immune system is a non-specific response. So we've talked about this, but things like our barriers. Barriers are always barriers. It doesn't matter what encounters them. They'll always work as a wall. Barriers are going to be found in the skin and all of our mucous membranes. So lining of the digestive tract, lining of the respiratory tract. We also have chemical barriers, things that also prevent the pathogens from making their way inside of us or for staying alive once they're inside of us. Things like acid, things like lysozymes in the eyes. And we've got cells that are going to be responsible or part of the innate immune system to help target and destroy pathogens once they've passed those barriers. So mast cells, things that secrete histamine, neutrophils that are phagocytes, macrophages that are phagocytes, natural killer cells that can then target virally infected or cancer cells. Part of the connection between the innate immune system and the adaptive immune system are our antigen presenting cells, so our APCs. Antigen presenting cells are things like macrophages, dendritic cells here, and in weird rare cases, B cells, but we're not going to worry about that for right now. Macrophages and dendritic cells are going to act as this bridge. So if a pathogen has invaded the body and it gets gobbled up by a macrophage or a dendritic cell, those will then make their way over to usually the lymphatic tissues and present certain parts of that pathogen to our T cells and B cells. And they'll kind of just show it around and say, hey, do you recognize this? Is it doing, do any of you have a receptor that fits this? If the receptor fits the pathogen's antigen, or that specific shape on that pathogen, that will stimulate the adaptive immune system to start its process launching the adaptive immune response. So it'll activate our T cells or B cells, causing them to differentiate into effector cells, cells that actually do the work. B cell effector cells are plasma cells that produce a whole bunch of antibodies. T cells will differentiate into specific either CD8 or CD4 T cells, so our helper cells or cytotoxic cells, and then those can then go and do their work. T helper cells activating other cells, cytotoxic T cells targeting and specifically destroying infected cells. So lastly, something I failed to mention, kind of the speed difference between the adaptive immune system and the innate immune system. The innate immune system it tends to be pretty fast in its response. Cells are usually pretty close or present. When a pathogen makes its way past the skin, there are dendritic cells right under there waiting to attack. The adaptive immune system, though, takes a little bit more time. So we usually tend to call this a slow response. That slow response or the reason why it's so slow is these antigen presenting cells actually have to make their way to another tissue, and then they have to kind of present that antigen to a whole bunch of different cells until it finds the right match, until it finds a T cell or a B cell with a receptor that fits that specific antigen. So that process can take a couple of days to weeks, depending. The adaptive immune system is a slower immunity, but it is able to recognize antigens that it's already seen previously. So we tend to say the adaptive immune system has memory. The next time that the body encounters this antigen or those immune cells encounter this antigen that it's already seen, it's able to deal with that antigen much more quickly. It's able to mount an immune response. It's able to protect us from that specific antigen. If I haven't already defined the term immunity, it just means the ability of the body to recognize something that's foreign and neutralize it to prevent it from hurting us. There are a couple of ways that we can acquire immunity. Two main ways. There's an active way and a passive way. So in active immunity, like right here, our body recognizes an antigen. It mounts an immune response. Our cells then will look at that antigen, produce memory cells that are going to then remember that, and will start producing effector cells that can then take on that antigen, hopefully producing antibodies or mounting T cell response to destroy that specific antigen. Passive immunity is a little different. In this case, the body is not going through all of the steps to produce new immune cells, new memory cells. What's only being passed is the actual antibodies. These antibodies can still recognize foreign material, but once those antibodies are gone, there is no memory after that. Both active and passive immunity can be even divided further still if we wanted to. We can have immunity that's naturally acquired or immunity that's artificially acquired. In naturally acquired immunity, like you get sick, you encounter an antigen, your body then undergoes all of the steps that lead up to the production of cells that recognize that antigen. You produce memory cells in response to it. You might get sick because that's what pathogens do, but the result is we still have memory being produced. And the body responds with targeted antibodies. So these are going to be my antibodies here. Active immunity that is artificially acquired is called vaccination. So in this case, a live pathogen is not present. Usually we take something like dead fragments of a pathogen, or even what we call an attenuated pathogen, a pathogen that's been like shocked, so it's weakened, and then we inject that into somebody. The process is going to be still the same. That pathogen makes its way into the body recognizes it through antigen presenting cells, presents those to T cells and B cells, leading to the production of antibodies and memory cells. The goal of vaccination is that you get the same response as naturally acquired, or at least close to the same response, but you didn't have to get sick in order to get it. And that's a good thing. Sometimes getting sick for certain pathogens has a risk of dying, which is not great. So vaccinations help to reduce that risk of dying, but we still end up making antibodies and memory cells for later. Passive immunity, we can also gain naturally. Naturally acquired passive immunity, just antibodies that pass from, say, mother to fetus through the placenta or through breast milk. The antibodies will circulate around. They can still attach to specific antigens, pathogens, little shapes. But once these antibodies are degraded, usually like 6 months-ish, then that immunity's gone. Like there are no memory cells to replace it. There's no B cells floating around. So once those antibodies are gone, the immunity's gone. So naturally acquired passive immunity comes from maternal sharing. Artificially acquired passive immunity, though, can be done by just harvesting antibodies from a donor, and that can be a human donor or it can be an animal donor, and then injecting those into somebody, and those antibodies will attack a specific antigen. During COVID-19, we used passive immunity as a treatment. Monoclonal antibodies were developed against COVID-19. They were taken and they were injected into people, hopefully to try and decrease some of the severe symptoms of COVID-19, and it kind of worked, it kind of didn't. It was a good idea, but overall, by the time people were getting injections with these passive immunity antibodies, it was a little too late, and the majority of the disease has already taken place. So if you were one of the lucky ones who kind of like immediately once you got sick were then injected with monoclonal antibodies, they did tend to see a increase in efficacy with that. But by the time most people realized they were sick and went to the hospital and stuff, they were already past the phase where artificial antibodies or artificial immunity granted by antibodies was super useful. So